although I won't jinx it by writing down an archive number with a couple of X's, because that usually push it down the line a couple of marks. I won't do that. It's in the collaboration with Dan Thompson from Swansea and his student Louis Cole and another postdoc in Brussels, electromagnetic. And the title, as it stands now, in the draft is very long, so I don't think there will be a title, but it says a title indicating a covariant assorted thoughts on geometric quantization, Chern-Simons, and boson individuality. So that won't be a title, but basically it's about various points of connecting Chern-Simons theory and Chiral boson in various incarnations. So I will talk about that and then maybe give you a couple of points about what we're actually doing. But first, I will motivate it from more general perspective, just maybe not necessarily in the paper. So, okay. So Chiral boson and other theories. So Chiral boson in some incarnation is ubiquitous in physics. So we can see it in just as some Chiral edgemons in quantum matter theory, for instance. We can see it in fact B string as a subdual form. It can be also seen in covariant formulations of string theory as a harmonic. It always shares the same idea. So in the most stripped down version, it's really just a theory where instead of having branching, this would give you a equation function like this. Which can be, and in particular, this is one of these operators still defined, right? But you can have, so this is non-Chiral theory. It has both left movers and right movers. Chiral boson, on the other hand, has only equation of motion, which is either phi plus 0 or phi minus 0. Okay. And as such, it has a huge symmetry. So this thing, if you look at it, if you shift it by any function of so this is a solution written in the form by left. That's not it. And here it's really whatever killed by del plus, right? Where here is whatever killed by 2 minus, so it just picks out one of these. So this is the most vanilla Chern-Simons Chiral boson. In fact, in B string, what I have in mind is that you can see this B field. So this is a 2 form. I'm sorry. You can see the.
Can you remind me? Is this also what I think Jakub talked about when they call self-dual boson?
Yes, I will review all these other formulations of the Chern-Simons.
Okay.
There's FJ action or formulation by Siegel, and I'll get to those. Just want to give more versions of this first. But basically, this kind of always works. If you wrote this more geometrically, you can think of d phi as one form, right? One form. And then this equation of motion is basically Laplace on this one form, right? Sorry, on this phi. Right, so this can be so written like that. You can just see this. You can have these equations And if you replace this by a form, or you can generalize this in any dimension where you can you can have like any form in any dimension you want. But the knowledge of this only works in specific dimensions for specific forms. So namely for one form in 2D. So this case is one form in 2D, right? And for one form in 2D, I can add this special shortening condition, which tells me that A is equal to star or plus or minus. Okay. And that cuts down the representation down and gives me just a Chiral boson. I can do this in higher dimensions. There's some restrictions. Basically, for any half form in even dimension, if I don't care about reality, this similar theory would can be studied. And so in type 2D, I have 5 forms. So I would have F5.
I wouldn't call it A. It gives the wrong association. It looks like potential, but this is really the filtering. It's a one form filter.
Yeah, that sounds better. F1. Thank you. Yeah. So same here, right? I can intend right? I can have 5 form with down by self-geometry condition. Right. So that's another realization. I can do the same thing in 4D Maxwell, right? I can have subdual instantons, for instance. Another slight change of this is in twisted subgeometry. So I'll explain that a little bit. So so these are all basic types of subgeometry. There could be also a setup where these forms, they have some internal index. And so imagine that you would have unspecified weight here, which in suitable dimensions so that you get the same form. But imagine that this had another index I. Then in principle, you can add another operator here. Such that if it squares to 1, it gives you so-called E-twisted self-geometry condition. And these also play a role. For instance, in Hall's covariant the covariant model for a string. So Hall's covariant. You have a model like this, so you would have a model which I'll explain what this means. You would have a model like this, but then it's supported by a constraint of this sort. So here you have, so this fat X or double X, it's twice, so normal Polyakov would have, say, 10 embedding coordinates. Here you have twice as many, but they're cut down by some twisted self-geometry constraint. Right, so similar setup. So all these models are very similar because they always have this condition, right? And there. And this condition is problematic. If you want to do anything else beyond just writing down the Lagrangian metric, then that problem is solved. And so, for instance, if you want to quantize this condition exactly, I will explain how ugly. If you if you want to write it out, it always turns out to be somehow breaking Lorentz invariance. So even if you can quantize, you usually need to break Lorentz invariance, and then if you want to do any sort of calculations, you run in troubles real fast if you go to higher loop corrections. I've seen some calculations done by them actually in Florian and Jackie will explain which one is that. And those calculations are transferable. So usually we want that Florian invariant. It's not just that people say that we want Florian's invariance. It really helps. And okay, so I'll try to explain first what is a problem with this constraint and how people try to resolve it. So I'll only restrict now to this chiral boson in 2D because that's stripped off of all the extra indices, but it still has the flavor of what is happening, and explain what is the problem of that constraint and how it's been resolved in the literature so far. Okay, so a little exercise to start with. We have again and right. So with the normal Lagrangian, then we would have say pi and pi coordinates in our phase space, right? These will be pi dots, and we would have maybe some total two. Okay, right. Now, so right, so we have this phase space, but it's cut down by a constraint, by this constraint, one of these, which you can see that they really originate from d phi. It's also minus star d phi. Right. So if I write it out in terms of the phase space coordinates, it will be phi dot minus phi. Okay. I'll call them sequence C-minus. And usually when we want to quantize, we first analyze these conditions and see as to whether they are first class or second class. Right? First class, if they're first class, we're happy because they generate gauge transformations. We can proceed in a TheorTea when you quantize the system, and of course in these convolution by a TheorTea differential. If the second class, we need to reduce the space, so it is down. Well, and usually that's much uglier because that renders the bottom bracket into reduced space non-polynomial right hand side. That's what would happen here, and it's hard to quantify.
So you're using some kind of covariant notion, because usually, I mean, if you talk about the traditional Dirac first and second class of constraints, then Dirac assumed that there's no, that we have done a total Lagrange transformation, got rid of all dots.
Oh, hang on, what am I doing? Oh, sorry, this is the prime.
Okay.
Sorry, this is delta. This is prime.
Okay, I'm next. Okay,
thank you. Yeah. Okay, but yeah, if you calculate, so now, okay, so what does it mean for a constraint to be first class or second class? First class is basically when you say you have a bunch of constraints, right? CI, if you calculate all their brackets among themselves, if this vanishes on the constraint surface, it's first class, right? If on the other hand, so generally there will be some matrices like J here. If that is invertible, then we call them second class. It can also be sort of both at the same time, and then we need to separate the first from second class. But here it's just one constraint, either C plus or C minus, and they're both, so both of these are second class. Both of them are second class. So actually, if you look at it, this gives you right. So then, yeah, you're facing a phase space with a second class constraint.
but then again, so we're in 2D, right?
You're 2D.
So I guess the delta function should just be a one-dimensional spatial,
one covariant.
and also
So
the
it's just sigma.
and also the covariant, the
Sorry.
the 5 pi one should also be.
Yes. Okay. Yeah. Yeah, it's in way, but even time. Yeah, and that's the derivative of that. Right. And okay, so then you have this second class constraint, and it's a terrible second class constraint actually, because so you can as I said, you could perform a direct procedure, but then you're breaking Lorentz covariance and you're not really able to quantize it in a Lorentz covariant way. You can do two types of tricks now, and that sort of distinguishes two lines of research which have been trying to work with this model. So you can either do a smart trick or do hard work. So what are these two things? So smart trick is to do Lorentz equal to realize that well, this is not second class, but sorry, this is not first class, but this is first class. So if you square the constraint, it actually generates a first class constraint. And then you can write a model which realizes this.
Is it obvious that it's second? So if you square this first class,
If you just calculate this, you'll see that you can get 0 right hand side. Sorry, you don't get 0. You get something proportional to C plus.
Well, you have to do a little bit more work. I mean, we don't know what happens with the C plus C minus. We don't know. Yeah, C minus will work in the same way, but what about the C plus C minus?
Well, there's no C minus here, right? I'm just taking out either solver or this.
Oh, we just put on one constraint.
Yeah. If I put both, then I have one right.
Okay.
Yes, this I don't know. I mean, it's a little bit dangerous. I mean, this is well known that if you have a constraint, then you wonder, can you square it? And
yes.
and for technical reasons, we usually don't allow that because we want the gradient of constraint to be non-zero for technical reasons.
I agree. Yes.
And that you destroy with this.
I agree.
you can always apply.
Yeah.
So just anytime you have a square, you can always get something.
That's true. Yeah. That's true. Yeah.
It's a little bit suspicious.
And it actually bites with the S. So I'll tell you how. Is it true that always when you square constraint, which is second class, you get a first class? Yeah, I never.
It works if you have one.
Yeah.
You only have one. But if you have two, it might not, because then you get if it would take C plus squared with C minus squared,
Yeah. Okay.
then you would get C plus C minus.
I never tried for anything else. I guess square and stuff because it feels very ill, as this Bob was pointing out.
Right.
And then indeed, it actually renders the problem even worse here in a way. Because so you can write Lagrangian and it actually corresponds to gauging some symmetry, which must be generated by this first class constraint. But when you start quantizing, you run in trouble. And what I mean when you start quantizing, you run in trouble. If you look at what this generates, it generates a shift of your field, but those gauge parameters are themselves constrained, and so you have gauge for gauge symmetry. And if you look at that, if you analyze the gauge for gauge symmetry, it will be again some sort of subgrowth condition, and then so you can introduce this gauge for gauge, but those gauge for gauge fields, they will have their own reducibility, and this will just continue to infinity. So if you want to quantize the system, you can, but you need infinitely many ghosts for ghosts and resolution, and it's just terrible, right? So nevertheless, that was the best thing people had.
So it wasn't a smart trick.
Sorry.
It wasn't a smart trick.
It's smart as in like you can write down the Lagrangian, I guess, and you can massage it a little further and make it look covariant, but not really suitable for optimization as it stands. Yeah, so not great. Yeah, not great. And this model. So there's various incarnations of it. I guess it first starts with Fourier HMP. to give you some historical background. So it looks like this basically, no, minus, it doesn't matter, but this would be the Fourier-Chakiv Lagrangian, which has gauge symmetry. It's terribly Lorentz non-covariant, right? So this confirms in itself, right, by Lorentz symmetry, but this one doesn't, so it gets formed.
Is it a sigma? Or what is
Sigma, yes. And then it's been, this model is such that it has that gauge symmetry. If you add the gauge field, you can make it a little nicer. You can write the Siegel model. And the Siegel model has a maybe more uniform, which looks like this. Still runs more covariant, but you have this gauge field in it. It's the Lagrange multiplier which enforces this constraint. I guess the C minus one, but yeah, it just chose C plus before. It's same for C plus and C minus. And if you use the gauge symmetry to fix this H to 1, you end up with the previous model for Chakiv. So that's the model. I will go back in this line of thought. How you can make this more covariant. But for now, I'll explain what's the other trick, or that's not actually the trick. That's the heart of it. So this can continue with some other models, which sort of resolve the form of H.
Right, yeah, so you put H to 1, maybe that was what you just said, then you.
This H You can also, if you started with just plain 2D boson and engage that chiral content metric. So how do you actually get this model? This model you can engage the left or right conformal symmetry. So you can you can gauge either of these, and you end up with Siegel, either for this constraint or the other. It's a little application, but it works. Okay, so the other trick is much more appealing, but maybe less well known. But people usually resort to doing something like this, but I don't think it's ever like successfully combined these models. People make it there.
You shouldn't use a wet.
Yeah. Okay. Next time. Maybe I'll use it.
Well, but we have the winners, a million of them.
Yeah.
One is sitting there on the.
Sure, I didn't prepare it there. Okay. Yes. So what is the trick number 2? Trick number 2 is the key is C plus. So you keep it, but it's second class, and there is this procedure of conversion. And the conversion is the trick where you add extra degrees of freedom and perhaps make this in the first class. And then if you have first class, you can gauge. Okay? But okay, so how does that work? I'll just it's a limited procedure. This was basically realized by McLean. Will you McLean, they just did this procedure. So
what year?
Sorry?
What year? I mean, approximately,
This old paper,
approximately.
not these.
Okay, the conversion,
It's maybe older even. but I
yeah,
don't know.
I mean, Bertale talked about conversion in the mid-80s.
Okay, wait, let me see. I don't know. I'll find it
Yeah.
later. It's an old paper. It's an old paper.
Yeah, Fatkin and Bertale, they did this in '88.
Okay, yeah. Then it would make sense that it's not used. Yeah, but here, so what do? So I will start with the same pi, and now I'll edit an index node. So this is my original field content, and I have this constraint, that I have this constraint C plus, which is pi prime plus minus pi.
Well, plus minus.
Yeah, just and so I can now do the following. I will add a pi one and pi one, and now I will take this constraint.
Are they also conjugate?
Yes, yeah, it's again like a free boson, and I will construct this zero C plus, which will be the original C plus C minus one, basically. It will be anti-cellular constraint for these guys, right? This one with the minus. Okay. So if I do this guy will be first class. You can see for yourself. There's a change of the sign in here, and they will cancel out, and you get zero.
What?
So it's first class.
Why did you call that C1?
Oh, just because it comes from this first.
Oh, that's,
layer.
oh, okay.
Yeah.
But then you should call that C plus C0. And the
Yeah.
new one C plus. Right, that would make more sense.
Yeah, it's not a great way to call things. So this is
This is just C plus, new C plus.
so this is the C plus, right? It's the old.
No, but then you shouldn't call it C minus, minus one. Because the one refers to which pair you're using. And if it refers to which pair you're using, then you should be called it.
I don't want
C
to,
plus.
because the other one, I want to make, okay, maybe I'll call this one kernel C. How about that? Because those will be the ones I want to use, and the little c, they will be just the ones for these pairs.
Yeah, so why would you put a one there? Or a zero? Then you just have to write more things. The thing you want to use, you should make as simple as possible. Just C plus.
Well, I would keep it C plus, but you don't know what's gonna come now. So I need an index actually. I need some extra index. I'm spoiling it a little bit. Sorry. But okay, I'll make this first class. But then it turns out that this is constrained again. This is constrained by the C minus if I want to recover the same dynamics at the end. So I edit this stuff, but I need to add this C minus as an extra constraint. So so what did I do? I had this original field content, I had the second class constraint, I added these fields. I made the first class constraint into sorry, I made the first constraint, which was second class, into the first class, but on the expense of adding this second class constraint for the second pair.
Okay, so one more time, what does the one mean in C1 minus?
See, that's just that this thing constructed. So, sorry.
It means that it will respect to one.
Okay, now I'm spoiling a little bit what will happen, but I will call this.
Yeah, but you just started by going away from this convention. if you're using this convention, then that first C plus is C plus 0.
Yeah, okay. I didn't want to use it because before I didn't have curly C.
Yeah, but you're,
No, it's
here you said, that's how it's going. Yeah, now it's fine. Okay.
I mean, here it was fine, I just said what it is.
Just didn't make sense.
Okay. But nevertheless, this is first class, right? This curly C. But I need this to kill that to reduce down the original system. And so I just pushed this problem into another level, basically, to extend its space. Well, but I can actually proceed and introduce phi 2 and phi 2 and make this one the first class, but I'll introduce another second class constraint. And you can see where it's heading. I can just keep doing this process and just extending my space to n-dimensional multi space. And by so doing, I will end up with infinitely many fields and infinitely many first class constraints. That seems terrible, but it's not that terrible. But it's much more honest than squaring the constraint. I mean, right? Like, who said that I can do that? And as you pointed out, it's not really a good idea. And you see that even if I do that, even if I disregard all those red lights, I run in trouble because it's infinitely reducible. This is much more, you know, constructive from scratch from what I start with the function and make it into. And then you can write a model, which looks a little horrible because it has infinitely many fields, but it has just first class constraints, and you can maybe see it in the paper because it's just little. Okay, but there seems to be a third way to.
Just one comment. I am a little bit rusty about what I mean. So what the Tartan and Patkin was in general theory.
Yes.
They proposed how to get rid of second class constraint and turn them into post.
I don't even know this general theory.
It was general theory, and not some specific like this.
Yes.
So, but as I recall, I don't think they had to repeat this infinitely many times. I think they only introduced final number of fields in this construction.
But yeah, that's the thing. I don't.
So what they did is a different conversion procedure than you.
So you think I mean, I don't know. I didn't try their way.
Yeah.
But I don't think they claim that it truncates. Do you know that it stops after? Because
I must admit I don't remember the details right now. But that would I assume right. I vaguely remember that it was that just made the phase space twice as big.
yes, but there's a problem. I mean, you know, probably more about constraint quantization, but from what I learned from Hamilton deploy, is that you have this procedure where you start with the system with second class constraints, and now you can start correcting the constraint, right? You introduce new degrees of freedom, and you write this expansion for the new constraint in terms of the new fields. But you're never granted that this new set of fields is not constrained itself, right? So in principle, you can correct, but then you might run into the same problem. And here you indeed you just have to repeat the procedure. And I don't know. Maybe
right. I think they were not so careful with respect to locality and the structure of space time. So for instance, this derivative. So it might be that they were not careful with that, and what you're doing is to make sure that you, for instance, have locality.
I don't know how that would. Do you think it would help if I do a locality, like I can truncate to the certain amount of fields?
Perhaps.
Yeah, I don't know how to do that completely. This was their way, my claim way. And it seems to mimic from what I understood from what their procedure. It's just that you're never granted what happens at that new level. It's just that, right, like I was forced to add this.
But in no entitlement, do they discuss conversion?
Sorry,
In no entitlement, do they discuss conversion?
yeah,
In the book,
yeah, I think so. There's a, wait, it was either in the book or in one of these shorter notes of, which one is it? Of Hannah. Maybe I read it from there. There's also this like lecture notes.
Right, that could be, but
That conflicts in my mind.
I don't remember the name in the book.
Okay, then it must be the other one.
Could be, it's 400 pages.
But yeah, okay, I don't know, but I bet if they, if it worked, it would have been understood by a lot of people. And I don't really, and but you anyway will end up with some implemented fields, either goes or method fields, or some auxiliary fields in your system. And okay, but there's a third procedure you can undertake, and which will give you some kind of Chiral boson. And that's what I want to talk about. It's basically the basic stuff. So these are two ways. So it's
kind of algebra do you get?
uh,
What kind of algebra do you get?
you mean for these constraints? There's just infinitely many commuting constraints.
Well, do they commute or do they give you some other stuff?
They give you what happens? They commute because they.
Essentially, you're saying, C's with different indices commute,
Yes.
and then you're sort of just taking care so that the ones with the same index, but they cancel some, they give you some, when they commute, they give you some contribution that cancels from with some contribution to the guy with some other index.
I guess there's a sign difference between Boston.
Yeah.
Configuration and that and so on.
Right. So. Okay, so it's just an infinite dimensional abelian.
Yeah. Which is sort of shifting them in a telescopic manner. So okay, but this is so these are two approaches or two lines of approaches to the Chiral boson. Also in this picture, this other approach of Hutchinson of making type 2D Lagrangian work out on how fits more in this line of work rather than squaring the constraint. Although
And what happens if you try to quantize this? I mean, what's the problem?
it's well, I mean, it's I mean, they even write up the TheorTea charge. It's fine. It's just that you end up with infinite fields, which yeah, I mean, it's okay, I guess. And then you can but that's the thing, like they would write on the cube, and then they would say, oh, we can use all these constraints back and conflate it down to the original problem, which is phi 0 and pi 0. Not much of that stuff. It's just that, like when you start writing down the cohomology, you have to implement fields, and they need to use this OSP 1/1/2 algebra to sort of find the physical content in the Hilbert space. So it's little ugly in terms of finding more physical fields, and then but in principle, yeah, you use one here, you can quantize this. Huge instruction. Yeah, okay. But yeah, the third approach, which is much simpler and sort of gives you both of these at once, is to go through one higher dimension. Okay. So it turns out that if you have Chern-Simons, you put it on the space where you have a boundary. So in particular, how we engineered it was we have a disk and a line. We have a cylinder. And with suitable boundary conditions, you can realize chiral boson here. So that's nothing new. People knew this forever. Although what was known was just the relation to the ungauge gauge form of thorium, how to get that from Chern-Simons. And all these higher, more covariant models, they are not known as to how to obtain them, or they were not known from Chern-Simons, let alone the MacLane 2. So that's something that's like the first result we've established as to how you get these covariantized models out of Chern-Simons. Maybe just to quickly tell you how that goes for those who don't know the classical story with Chern-Simons. It's basically that you take your Chern-Simons, say just abelian, but it works for non-abelian as well. Which is also something I think after we realized that it works in covariant fashion for non-abelian case, these extra models I keep finding dots and not really the models, they are not even known for non-abelian case. And here Chern-Simons just spits out something for you. So let's just focus on the abelian case. So you have this model. And if you, what do you want to do? You want to somehow use a theoretic boundary. So there's a way, so one thing you should do is you should have a boundary term first. And it looks like this. This boundary term is only, this is boundary term which will first of all introduce some metric dependence of the boundary by a star, right? This was a topological action, and this is now non-topological, right? Breaks topologicals. Also, it breaks gauge invariance partially, because this was a gauge invariant in and of itself, as long as k is kappa is quantized. This is not unlike the gauge field is constrained itself. Okay, so at the boundary, this breaks gauge invariance. So if I look at a bar A and transform your gauge symmetry, I get E lambda. And maybe it's easier. Sure. So this basically enforces the boundary condition like this. And you see that this boundary condition is only preserved by lambdas which satisfy its locality. So this is partially gauge symmetry breaking boundary condition. And that basically, in the on Hall effect literature, they would tell you that these are exactly the modes which start propagating at the boundary. These like broken gauge modes are what creates the edge modes in the boundary system. Right, usually this is not added, but it's nicer because then it renders the whole system just so usually, you know, you would bury the Lagrangian and look at the boundary terms, right? Look at, and then try to fill them and get Neumann like boundary. Here, additional term like this exactly makes that type of boundary condition Neumann. Here, if you didn't add anything, you would be told that you should set this to 0, the boundary, rather than some combination, right? Some A tau plus plus a sigma. So this alters what should happen at the boundary and sort of makes it into a nice variational problem. Okay, but okay, so if you do this, you and you proceed in the similar fashion as you would normally do. You identify now dynamical fields. So we have your A, and so if this is tau, this is sigma, and say some rho which goes to the bulk. So sigma and tau are the boundary coordinates.
So the curve side of the cylinder. So not the ends of the cylinder, but the curved side of the cylinder.
What side? No, yeah, the sigma goes all through the.
Yeah, you mean when you say boundary, you don't mean also the bottom and.
No, sorry, there's no boundary. Yeah, just it's goes forever. Yeah. Yes. It's not finite. Maybe you do this expansion. Then you feed it in the Lagrangian, you find out, people probably know all of this, that this is not dynamic, right? It plays a role of Lagrange multiplier, and that Lagrange multiplier enforces a first class constraint, which looks like the following: R sigma rho. This is the first class constraint associated to this right? This is what you find in the Lagrangian if you do the splitting, right? If you take this and feed it in there, this is what you find. And there's nowhere to be found a kinetic term for a tau, right? Because of the antisymmetry of the epsilon ether, basically. So this only plays a role of the Lagrange multiplier. And then you can solve for that. So you can find some, so you can solve for this. If you're on the disk or in other star-shaped region, that's actually important. That's not just some topological nonsense. And you can solve this as a d sigma RD. So this will be your A verb plus so then, right, so this will be a sigma and a rho. We put it back in. And this whole Lagrangian just gives you boundary term. It gives you boundary term, and that boundary term will be exactly for your nature key action, this one. So that's very nice. And but how does it work for these more covariant versions of the TheorTea key that I'll also, and then maybe comment on how much time do I have? One more minutes. Okay.
If you want.
Well, if you want, I don't know. Right, so yeah, that's how it works for an energy key. Now I'll explain what's the most covariant version of this one. And how you get it from the project that we can measure like this. I'll also note here that this is pretty nice system, right? It's a system that is fast constrained, and people have studied its quantization a lot. So it's advantageous to maybe go to this 3D model and modelize that and then derive some quantum phenomena from there and translate them to 2D. And I'll explain why we did it in the first place. So just a quick.
So can I ask one thing? So A is one form, so star A, so you're taking the star with respect to just the boundary or?
Yes, that's very good. In Bob, there's no metric, and even if there were, it wouldn't work. It's just a boundary condition, so it's restricted to the boundary, and then star is applied, which is induced from some metric at the boundary.
So like star 0 is 0.
Star D what?
Yeah,
I mean, so it's AT now, A sigma, B sigma, and if you apply star on that, then one of them is will be 0.
Oh yeah. I mean it's already 0 when you maybe specify what the boundary range that's the boundary. So there's no row in the first place. Okay? You restrict them, you kill all the parts, and then you apply your star.
Okay.
Okay. So to these covariant models, so there's two, most notably ESD model and PST, which stands for Pasti, Sorokin, and Tony. And this model it's slightly covariantized Siegel's model. So what does it look like? It basically produces this extra weird term. So it's almost the same, except that you substituted this weird fraction for h, right? And that sort of renders it Lorentz covariant, but not quite, because you still need to require that this is non-vanishing everywhere, and what if you transform to the frame where it's vanishing, then it's not really allowed. So it's only some subclass of Lorentz transformations where this really
If you just wanted Lorentz invariance, why don't you just take d plus f squared?
D plus. I don't know, because it would not. So I mean, ultimately, you want also look at the equations of motion and see that they are giving you something equivalent to the original Floriani-Jacquet. Don't know if it would work with that. So this is something what has peculiar gauge geometry, few of them actually. And if you gauge fix, you see that that the dynamics is that of Floriani-Jacquet. And even if you don't gauge fix, you see that there's right amount of propagating degrees of freedom and they're sort of chiral. So I don't know if it would work the way you're
Probably not, because
probably.
that seems like the logic.
Yeah.
If it's just Lorentz invariant, then
Yeah, no. Yeah. It's still, I mean, all these like, they're gone now. But the Floriani-Jacquet, this hierarchy of models, they still should have the same dynamics. They're just,
sure.
you would have more fields, maybe make them nicer, but they still are the same in essence. Right. And so this has a weird gauge symmetry, which looks like following. One is Simon. Yes, sorry. So where Simon is some field. And the second one is this sphere symmetry. but this is a shift by any function of f of phi, and this is shift with epsilon being local function. So that's the PSD symmetry.
So what is the parameter in the second?
In the second one, it's just like a strange shift. Well, it's just shift by any function of lambda. Sorry.
Okay.
Okay. Yes. Yeah, lambda is a function of f. Okay, that's right.
So it's in fact infinitely many symmetries. It's like an epsilon 1 f,
Yes.
epsilon 2 f squared, epsilon 3 f
Except
cubed.
that those epsilons will be just well, not even like it's
Just infinitely many symmetries.
But this symmetry secretly actually is symmetry of say it right now. No. So yeah, each of these symmetries, if you use them, you can see that clearly if you fix this f somehow. You can get one here. You can use these symmetries to fix this to one, and you'll end up with covariant Chern. But you can also see that the level of equations of motion that the dynamics will change. There's one better model. So also this model, it's been noticed in the literature that it's as if you so covariant Chern is already in sort of Hamilton-Lagrangian form, and you pick the time. Here you're also picking a time. Okay, you're saying that this will be my time direction, and that will be the non-binary opposite lines. If you parameterize that choice of the time, you end up with PSD model there, and that's what we can do here. We can also parameterize that splitting. And if you do that, you end up with something in the PSD family. Not exactly PSD model, but we end up with this another model which comes by two names, which was first studied by it's a trick studied by Harvard. But also studied a lot by TheorTea. For that reason, and that's what we learned from, so we call that model.
There's a lot of.
We call it that model of this guy. We're not synthetic. Yes. And that model, so what's also weird about this is that it's non-polynomial, right? We hear like these statements in the literature that it can be either covariant or non-covariant, but non-polynomial, and then you can go a little further and just introduce extra trick and make it polynomial. So you can write this in Chern Lagrangian, and if you integrate out alpha from this, you end up with the same model. And you can also extend those two symmetries to this model. Okay. Right. Okay. So I'll explain how you generalize this procedure a little bit to obtain that model. So as I said, we just do the split for everything. That's all you need to know basically about it. I can write some words, but so what we do, we would take splitting. So we have this time, which is now tilted maybe, and it's given by some vector b, and there would be also dual form omega, which is closed. That would be some geometric input. Now you can take your T, which would be the curve plus the parallel, and so the parallel going to be this microcheck. And accordingly, you can also split all your fields as a parallel plus a curve. And so this, if you gauge fix this choice, so if you gauge fix then chose omega to be t, dt, that would be clearly closed. You would end up with that splitting to get up there, right? Well, because this is a parallel, and the A curve will be the remaining bits, and this will be the D restricted to the this. Okay, so if I do this, I would perform the splitting. I would feed it in the same Lagrangian, and then long story short, I can end up with that Mercian Lagrangian if I identify. So how I just need to tell you. Omega times like that. So this is the splitting we choose. So this is the one form. This is some function which multiplies the one form, which will play a role for the Lagrange multiplier. And this will be fixed. So here we will solve for.
I guess if you want to go to the static gauge, then if you want to go to the static gauge omega equals dt, then I guess you also put the vector field v to maybe be ddt.
Yes. Yeah. If you do this, then the v will. And so by solving this step, this will tell you that this guy should be some d per 5. So if you do this, you end up with the Mercian Lagrangian, where this will be the df. Okay, so it will work before you get that Lagrangian at the boundary. Okay. Okay, so that's great. You can obtain that most covariant Lagrangian people know in the literature from Chern-Simons. But what are those symmetries? There's two symmetries. One of that gauge symmetry, it actually comes out of the gauge symmetry in the Chern-Simons.
Which one?
The first one. It looks ugly in that form of PSD. But it's because you've integrated something out, so you kind of make it weirdly realized in that model. So that's what's happening. The second one is more interesting. Symmetry. It actually is some kind of zilch symmetry. So what I mean by that? So for that, I need to say that so Chern-Simons is already in a Hamilton Lagrangian form. It's just that we didn't spread that at the beginning, but so if we're basically right, what I mean is that we're quantizing Chern-Simons, we're not doing that Legendre transform. It's already in Hamilton Lagrangian form, and every system which is Hamiltonian has this strange symmetry, which is that if you take a stage and use it as a generator of the symmetry, so will be generator. That would be the Lagrangian. So Chern-Simons, for instance. I just mean like you need to pass to the. I just mean like SH by SH, something like this. Which Chern-Simons did, right? Of that form.
So should we call it L maybe?
Yeah, we call it this.
Yes, but, sorry. The full action, the integrated over. So I'm saying that this, so I'm trying to say that this always gives you a trivial charge source. And that's what generates that other symmetry. So what I mean is that every, the SH itself is clearly invariant under this symmetry.
You're integrating over all three-dimensional space or just
Over two-dimensional slice.
well, then it's SL. Not written L, but L.
Well,
If you're not integrating over time,
You mean L8?
LH. Yeah, you should call it LH, right?
Yeah. It's not the Lagrange, it's not the Lagrange set back.
yeah. So that will generate these numbers. And if you take this generator, and look at what it does to these fields, it will generate the other symmetry. So you get both symmetry sort of. Sorry.
And if they place it on the bracket, this is like an operator acting on something.
Yeah, that's a boson bracket. That's the one obtained from the canonical kinetic theorem of Chern-Simons. Right, because Chern-Simons, when I just write it out, and I will identify these to be dynamical fields, which are canonical conjugates. So if I have some boson bracket, and it's the boson bracket I'm using here.
Okay.
And that will actually give rise to the other symmetry.
so how did you get the lambda in there?
How do you get lambda? Well,
How do I say it's a full?
It's a
function.
It's a function, yeah. But this is a local symmetry, so there is a parameter.
Well, I mean, there.
But this is really not quite be a gauge symmetry, right? It's more like infinitely many vocals. Isn't it kind of like arbitrary functions?
Well, he's saying that the arbitrary function, then if you expand it in the Taylor series, there are coefficients and powers of it. And then each coefficient in there is a function of space time. No, so why is the coefficient of function of space time? So the lambda should depend on. Does lambda depend on space time or not?
Only through that.
Just the function.
Yeah.
Okay, so then it's global. Yeah.
Infinite many global symmetry.
Infinite many global. Yeah.
Yes, I thought you would see that exactly. You don't see that PST level very nice. I don't know. It's only when you divide with Gretchen in a different form that you see that. But I didn't do that step where you go back and need to look at that.
It's just Taylor expanding lambda.
Yeah.
The coefficient in the Taylor expansion.
Yes.
With no functions to this time.
Yes. Yes. Yeah. I don't know, show it straightforward. We could go to the number channel, another orbital, sorry. But yeah, but nevertheless, you establish like a nice duality between this model and boundary dynamics of the Merkel and our form. Right. It's just it gets all a little distorted. So these symmetries are much nicer at the level of 3D before you integrate out that constraint. But integrating out the constraint invests some other degrees of freedom, and everything gets weird. Like this symmetry translates to something weird, and the gauge symmetry itself translates to something weird. So it's all somehow.
By where do you mean this?
Sorry.
By weird, you mean?
Yes, yes. The sort of the origin of those happily, well, other people claim other origins of that. They can also get it from nonlinear sigma models somehow.
But the second symmetry is not weird.
Yeah, second is
It's just phi transforms into an arbitrary power of f.
yeah. Good.
Mm,
But the first one is kind of strange that
but you know, if you haven't,
The boundaries very.
yeah.
That's what we mean.
So,
If you only want that, you know.
yeah. Whereas here, like you just have the gauge symmetry, you can, you know, it's in 3D, it's weird, but you end up with something decent.
but if you have a global symmetry, then you have conserved charges. What are those? Infinitely many of them.
I don't know. I don't know what it means for the model. Something to be thought about. But, yes. Okay, so I would just want to say that maybe that's more involved, but this McLean-Weir model that can also be obtained from Chern-Simons. And it's obtained by not doing this integrating out. It's just that this integrating out, it actually makes everything weird. Like you start with metrics and then makes model, and this integrating out that it just makes makes a weird field redefinition, or it actually kills a lot of degrees of freedom of the original phase space of this model. How do you see that actually? Is that you can, if you take the Chern-Simons and the one with the boundary condition, then you expand it in the row direction. So you write it as a, like, you take your A, and now you expand in some again functions of row. Then it looks like as if you had infinitely many fields just looking at the boundary, right? With this extra thing which will be integrated out. So you already have some system with infinitely many fields living at the boundary, some two-dimensional system, with first class constraint, which is given by the modes of this Fn, right? The modes of the flatness in the parallel direction. And that turns out to be exactly after some field redefinition corresponding to those telescopic McLean-Weir first class constraints. So that's quite nice, and I don't think it has been seen in the literature. And furthermore, you can also wonder, which we didn't, but would be natural extension. Wonder what happens if you leave that parametric invariance of time, then you get something new and weirder than McLean-Weir like this, with infinitely many fields and first class constraints. So this way you can derive McLean-Weir with naturally infinitely many fields just from the expansion. And you can see that the first class constraint they have is corresponding to something geometric, to the parallel first class constraint. This is what generates the gauge symmetries in the analysis. Perfect. Right. So that we can also do. So basically we have the control over all these Chern-Simons, chiral models of boson, and we can obtain them from Chern-Simons. Why we did it? So because I'm done here with the calculating, not that I calculate, but I want to say why we did it in the first place, which was the motivation. This, we wanted to understand some quantum features of D-duality, and it turns out that there is this model, yet another model, which was introduced by Hulík, and that is that if you take now non-Abelian Chern-Simons, or non-Abelian Chern-Simons, you can generate E-model at the boundary. So E-model is some kind of model of a Hull type. So it's a model with twisted self-duality. So here you will take Chern-Simons based on a Drinfeld double to have a G Drinfeld double. And on Drinfeld double, you will choose
special Drinfeld double or any.
and so this construction is very arcane, but it's any Drinfeld double and some age of the you take on the Drinfeld double. I don't think for concrete models we usually went for SW2R or U to the 2n. So not very general models. So we want to start somewhere. And then you can construct a similar model where the role of these boundary terms will be played by this. Okay, so that will give you the twisted self-duality of the boundary.
This boundary term chooses the chirality for you. Also, the sign gives you. Switching the sign gives different.
Yeah, so this it's kind of it's not really so this is self-duality. What it does so this model doesn't give you carbon theory at the boundary, but it tells you so this basically decomposes the little g into left movers and right movers, and it tells you that the left movers will only be chiral and the right movers only be anti-chiral, and then it couples them together. So that's what happens here. It's more like a Hull model, right? It's also not chiral really, because it tells you that the left movers should be chiral and the right movers should be anti-chiral.
And if you flip the sign, you get the opposite.
If you flip the sign, you get the opposite. Right. But there's an extra condition here. So this is not the full story. This will sort of give you double model, right? At the boundary. You need to kill half of the G, and you do it by gauging. So this condition you put on one side, so you put one condition here, H, and that gives you a model which has this channel metric in it, but it still keeps all the degrees of freedom. But you need another boundary condition here, which singles out H. Letters are K, subgroup of G, and it imposes some condition such that A restricted to the boundary G, second boundary, who lives in K. So this bubble would call the logical boundary condition, and this is some physical boundary condition. Physical because it really has some notional of metric. It's as if you put this 2D metric there and wrote into logicness. Whereas these boundary conditions, they just restrict the field to some subalgebra. And if you do this, you will effectively gauge this K out of the model. And basically then T-duality is realized by choosing different Ks here, different isotropic subgroups, and engaging different subgroups here. And our original motivation was to not study this T model because that's kind of ugly and non-linear, but to study the Chern-Simons and quantize that. We kind of know now more. This sort of came out of understanding Chern-Simons and how it corresponds to different chiral models. So now we know more about Chern-Simons and how to quantize it, and we could basically implement this at the level of Hilbert's case. So you can quantize your Chern-Simons, and then cut out part of the Hilbert space, which corresponds to some T-dual frame, which is given by this topological boundary condition. And so kind of find different dual subsectors of your full Hilbert space, of full doubled model. So that's the original motivation for this whole project. You have some more quantum understanding of T-duality coming from Chern-Simons. And yeah, so I think I'll stop here because so that's time.
So do you still have the symmetries here?
Yes, but there's more gauge symmetry reduced by the.
Well, of course, you have the gauge symmetry of Chern-Simons, which should reduce to some symmetries like what you have there on the boundary. But do you have also this, what do you call them, zilch?
Yeah.
You have,
Yeah.
does it look familiar in any way?
No, but the model, I mean, this gauge key model is not something, I don't know, that we'll study. I don't know if anyone noticed those symmetries in that model. So, I mean, they're just ugly symmetries, and
Well, they didn't look so ugly. And
yeah, I don't know what's the meaning of it. I mean, they're technically there. It's the same. It's similar setup, but I don't know. I don't even know what it means for that model. There, it's really something.
So what happens now if I choose gauge group SU2 times SU2 in the bulk, and I do Chern-Simons, and on the boundary I get some left movers. Well, okay, I have to. I mean, can you say something about ADS CFT?
These are different than boundary conditions coming from.
Well, the boundary condition here, you sort of select one sector, left movers or right movers.
Yes.
But you could look at both. You sort of claim that it's harmless. You just put it into choose one. But could you say something about CFT, ADS CFT by these kind of technique? Just study one sector, let's say.
I think I mean people do the like 3D gravity and Chern-Simons form, right? But the boundary condition there is slightly different still. It not only has this killing of the chiral sector. So in ADS-free safety you have two Chern-Simons, right? You have, for instance, SL2, SL2,
right?
And you take one, and so you have those two sectors. You make one chiral and one anti-chiral.
Right.
But that would give you SL2 Katsumudi, left moving and right moving at the boundary.
Right.
But you need to do further reduction. You need to what's it called? Principle of reduction of those Katsumudis.
Right.
And that's done by extra condition on A that it has certain blow up at the boundary. And what it does, it further breaks that Katsumudi just to stuff generated by Virasora, which is one obtained from Katsumudi. But yeah, for that you need extra condition at the boundary. Not just that it's chiral, but the part which is not killed needs to go like 1/r. If you analyze the residual gauge symmetries of that, you see that they are not full SL2 Katsumudi living at the boundary, but you see that it's only one generator, which is Virasora 1. But yeah, it's very similar. It's just that you don't do that extra little reduction.
Yeah.
So you show this sort of correspondence between Chern-Simons, and you can generate all these different models that we were talking in the beginning. Does this Chern-Simons theory also agree with, say, quantizing the models? I mean, you said for this model, but for the previous ones, For the not polynomial.
It's not that, so the claim is that we should really quantize this.
Yeah.
Rather than those models. So it's just that we've seen that it gives rise eventually to that. You just want to quantize that, and
Yeah.
you don't really want to touch those because they're weird. Or little weird.
And that's something you're doing with.
No, I just like very basic things about the linear group and it's a process.
So how about self-dual two forms, or one forms in 4 dimensions, using 5-dimensional Chern-Simons?
That also works. We can do like a self-dual 3 form in 60, self-dual 1 form in 40.
It's actually a self-dual 2 form in 60, because
It's
physics,
sorry, field strength is three form. These.
Yeah.
That also, and if you can reconstruct that from 5 Chern-Simons. And likewise for live to be like you can basically write that as a 11 Chern-Simons. I think so as we were searching for this similar thing that Malvasan actually wrote this 5P and Malvasan wrote something very similar for a 5-frame dynamics, like you would say, we have 70 Chern-Simons, which generates the action of the 5-frame. And so it somehow has appeared in the literature that part of the studies studied. But you can also like McCurcheon, he studied this a lot and he has various covariantized versions of those higher form models. Usually like in models and elsewhere, it's not covariantized, it's just in specific age. McCurcheon, he would put it in the same form as the base state. And that can also be done in terms of it just works in various dimensions over the model. Yeah.
Nice.
I don't know if there's some, I don't know, if you can do similar double model there or something. Nothing probably prevents you from doing it.
Okay, any other questions? So let's thank for that once again. Next, and we'll put each other on Thursday at 10. Okay. Thank you.